Let's get started. I think that before the break, I briefly introduced the concept of oxygen carrier can be used for the nitrogen carrier for ammonia synthesis. So I think I spent almost 45 minutes talk about the combustion oxygen carrier, and now we shift to the nitrogen carrier for ammonia. So during the break, I download some picture I want to show you. So you can visualize and see the complexity of the chemical looping. Remember, in the last session, we talked about the combustion, right? There are two vessels, and then the solid moving around. So in reality, how this look like? So this is chemical looping combustion, and then this is really hardware, and this is just the pilot plant at the NETL. So since this is recorded line, you can anybody interested, you can just write down this website. You can see a lot of information combustion. And then obviously you see the two vessels, all right? 1 and 2, because the solid actually moving around. See the from the bottom to top to the other one, and then the top coming back. It's circulating. Okay, so this is really hardware. And by the way, this is not even commercial. You can see how tall this is the pilot plant. This built pilot plant demonstration. It's fully automated and engineered. I want the audience, the students, read the notes regarding this. Please read this. In chemical looping combustion, oxygen is created in situ. That means you do not need the what you call that, air to see the fuel. It's created in situ. Where is in situ? Oxygen is in the oxygen carrier. You are not going to directly have the methane of hydrocarbon interact with air, interact with oxygen, because that oxygen is in situ, it's in the carrier. Okay, so eliminating the need to separate oxygen from air. Remember oxy combustion, you had to separate from the air in order to do oxy combustion. Chemical looping is not oxy combustion, but achieve the same. Oxy combustion, you produce pure CO2. Here, you did the same. Remember the combustion, you still have a pure CO2, but using air. Okay, so I want to continue read. Eliminating the need to separate oxygen from air, reducing energy demand and the system cost. So energy demand, because this is really the fully integrated, and then there are a lot of the heat exchanging and then involved. So, but true. I don't think that this is this unit has been scaled up yet. I think the largest one I saw in terms of power generation is 50 megawatt. In the United States, the smallest power plant is 300 megawatt. I'm pretty sure in India, India built a very large the power plant. You are talking about probably over 1,000 megawatt. But the largest one in chemical looping combustion for power generation is only 50 megawatt. The one I'm showing you is a 5 megawatt pilot plant. This is not commercial. This is really for the demonstration, prove the concept of this looping. Okay, so all right, I think we spent too much time on chemical looping, on combustion, but really I want you to gain some knowledge theory, and then our real focus is here. The concept of oxygen carrier can be used for nitrogen carrier for ammonia synthesis. Remember for the whole week, last week, we are talking about the ammonia synthesis, and then the equilibrium control. That means nitrogen, hydrogen will never go to 100% conversion. And then they operate at 500 degrees C and 250 bar, because the temperature will increase the kinetics, reaction rate, and the pressure will shift the equilibrium to the right. All right. So now the question is chemical looping, which is shown here. I'm going to interpret it. Okay. So why chemical looping by segregate nitrogen activation and hydrogen reaction? That means the nitrogen and hydrogen do not see each other, and then we can operate at low pressure you think we can? Do you think chemical looping is subject to the equilibrium control? So chemical looping ammonia synthesis is called, remember, it's called CLAS in the literature. It's called chemical looping ammonia synthesis, either called CLAS or the CLAS. Do you think CLAS? Two questions. Chemical looping, why you can operate at low pressure? And do you think the CL is subject to equilibrium limitation? Let's discuss. Say something to the audience. If you understand, or you just say I don't understand, that's fine. I'm going to interpret this the loop anyway. Anybody has any answer? Just answer. Okay, go ahead.
Chemical looping ammonia synthesis. So this equilibrium talks about, you are talking about chemical equilibrium. You are talking about chemical equilibrium.
Could you repeat what you say? Are you asking my question or you are answering my question?
No, I need some clarification on your question.
So just answer yes or no. Do you think CLAS, chemical looping ammonia synthesis, like loop shown here, is subject to equilibrium limitation? Just yes or no. That's all I need to know.
Yes. Yes, it comes under equilibrium limitation.
Okay, so if you put the nitrogen, hydrogen in a reactor, they're together, okay? Like this reaction. Oh, geez. So in this vessel, you have nitrogen plus hydrogen form ammonia. It's equilibrium control. Keep in mind the key words here is nitrogen, hydrogen, they are together, okay? They are in one vessel, they collide each other, they react. That's subject, this reaction, the hydrogen, nitrogen, they are together. They are subject to equilibrium. This is 16. Now, if you look at this 16, did the nitrogen and hydrogen meet each other?
Meeting directly.
Yes, not directly, all right?
Not directly. Yeah, with the aid of metal nitrates.
So if they don't, if they are not meeting if they don't see each other, why do you believe they're subject to equilibrium? Because you have two. Here you have one equation, and here you have two equations. One on this side, and the other is on left side. Two reactions, and then each of this is one reactor. Reactor 1, reactor 2. In reactor 1, nitrogen did not see hydrogen. In reactor 2, hydrogen did not see nitrogen. So why do you think the whole system is subject to equilibrium? The answer is no. Okay. Do you think the class is subject to equilibrium limitation? The answer is no. When you answer no, you can answer the question on the chemical looping you can do 1 bar because it is not if it's not equilibrium limited, you can do low pressure. Only when you are equilibrium limited, you need to increase pressure. Remember, if you increase the pressure, they go this way, all right? Because you have 4 molecules on this side, and then you have 2 molecules. In this system, the hydrogen nitrogen, the traditional Haber-Bosch process, if you increase pressure, will go this way. Here, you increase pressure doesn't help you because nitrogen, hydrogen, they don't see each other. They present in the 2 different vessels. Make sense?
Yes, sir.
So, okay. So I'm gonna flipping back to the how similar this one, the diagram here, to this. You don't think it's similar? Here you have this oxygen carrier, which is the iron oxide and iron. So basically you're shifting between right? It's called oxygen carrier. So basically you are shifting between these carrier, the different oxidation state. Okay, so that's basically the allow you have air and the CO2, they are segregated. CO2 is in one vessel and air is in, nitrogen is in another vessel. So that means nitrogen and CO2, they never see each other. Okay, remember we did the exercise. If you have nitrogen and CO2 see each other, you'll be in trouble. All right. So now, so that they don't see they. Let me go back. If you have nitrogen and hydrogen see each other, you cannot separate unless you go to 340 bars. Now the similar idea here, you know, you have this oxygen carrier. Now I have a nitrogen carrier. So nitrogen carrier represented as Me. So in this side nitrogen, and then react with the nitrogen carrier and become activate, which is called Me. What do you call that? No, this one. On the left hand side is the second reaction. Okay, I'm going to highlight. Basically, you have MEX, Y plus nitrogen become IE-NY. This is called a nitride. So the nitride going to the other side, react with hydrogen, and then the nitrogen come out and form ammonia. You see the ammonia come out, all right? So basically, first you have, let me leave this. First, you have a nitrogen react with this carrier called the nitrogen carrier, a nitrogen carrier, and then going to the other side, react with the hydrogen. This, by the way, is a solid, very similar to combustion, and then react and form ammonia, and then coming back, and then go to react with nitrogen again. The same material coming back and forth. It's the same as the oxygen carrier, but and then here is the nitrogen carrier. It's much more complex than oxygen carrier. Oxygen carrier, you can use the iron oxide or different metal oxide. Here, you have to use a complex the metal that can form the metal nitride, and metal nitride react with hydrogen and together. So the point I try to make is on the right hand side is hydrogen react with a solid. That's why it doesn't subject to equilibrium because the gas and solid reaction with nitride. On the left hand side, it's a gas nitrogen react with another solid. So both reactions on the left and the right hand side is looping. They are not subject to equilibrium because only when you put hydrogen and nitrogen together in this vessel, you are subject to equilibrium. But when you separate them, they are not. So that's why you can operate at 1 bar and then some of the temperature between 450 and 800 degrees C. And the temperature range depends on how active you metal nitride. So the more active, the lower the temperature. Make sense? So anybody has any question? I mean, that's why I spent so much time to talk about the oxygen carrier. Now the same concept applying here. All you need to do is you just circulate the nitrogen carrier around. Okay. All right. Go ahead. What's the question?
Yeah. Yes, sir. One question, sir. So actually, with the aid of plasma, we are generating ammonia in ppm level only.
I think at the end of today, maybe I don't have time today. I'm going to talk about how we form the nitride, metal nitride using the plasma. That's different, okay? So yeah, with the plasma, you do not need 450, 800 degrees C. So I do have slides showing you microplasma. That's why today I'm talking about the chemical looping and also the plasma. What is advance of plasma applied to ammonia synthesis? It is the plasma chemical looping. So very good question, but I have answer at the end of today, maybe tomorrow. So basically, you form plasma, then put on you the what you call that, you the looping agent, and then do the chemical looping. So let's save this to the end. So actually, I have a PhD student that did all of this. Yeah. But I want to walk you through this very slowly. That's why I spend so much time give you background chemical looping, because in last session when I started, I realized some of the students even have no idea on the chemical looping. So I slow down, talking about oxygen carrier. Now I'm talking about nitrogen carrier. But you asked a very good question about plasma. Plasma will enable this process, make it more easier. Okay, that's plasma. But plasma will not change the concept. Even if you are plasma, you still need a nitrogen carrier. Only difference is the plasma will make it easier. That means you probably don't need 450, 800 degrees C. Actually, my student doing this reaction at 250 degrees C. So that's different story. I don't want to pre-contaminate you. Let's go step by step. Do you understand the chemical looping shown here, everybody?
Yeah, yes, sir. Here, absorption is fine, sir. Nitrogen is absorbed by absorbed, and afterwards, hydrogen is we are sending. So what about the conversion rate, sir? Here, nitrogen is captured in step 1, and then nitrogen is reacted with hydrogen. So the excess hydrogen will come out.
Yeah. So nitrogen flow in. There's excess nitrogen coming out. It's fine. So you flow nitrogen and coming out fine. And then the hydrogen here, you never the idea here on the right hand side is form the metal nitride. Nitrogen coming out is fine, but it's from the different reactor. Then you move the solid metal nitride into another reactor, then flow hydrogen, the ammonia come out. You follow me? Yeah.
Yes, sir. With the ammonia, hydrogen also will come. Unreacted hydrogen.
What you say? What?
In the second sample, unreacted hydrogen also come along with nitrogen. But it mentioned only.
Why hydrogen come with the nitrogen?
No, sir. Hydrogen come with ammonia.
Yeah, with ammonia, yes.
Then again segregation is issue, because again segregation issue will rise there. So we previously discussed ammonia with nitrogen or ammonia with hydrogen.
Okay, I see the. Let me draw something. So good question. Let me draw something. So I hope you understand. Okay, so nitrogen. I think I hope this answers your question.
Yeah, nitrogen is fine, sir.
So nitrogen is recycled. All right, so bear with me. Let's go to the hydrogen. Let's go to hydrogen side. Okay, you need a separation. So basically, on this side, let's just oversimplify this. Okay, you do have hydrogen coming out. Okay, you do have excess. You're talking about.
But segregating hydrogen and ammonia is difficult.
No, it's the same. It's the same separation. It's basically separation ammonia. It's low pressure. Well, today's day 6, day 7 or day 8. I'm gonna talk about the low pressure ammonia separation technology. Okay, so you can separate the separation and then and yeah, low pressure. Basically, you need a solvent. Absorbent to separate the ammonia is come out, but it's very separation is no problem. Okay, so the problem the problem this loop solving is you never have hydrogen and nitrogen see each other, then you are not subject to equilibrium. That's the beauty of chemical looping. Separation is given. You can use any technology to separate. Okay, so I think your question is about the cost. That's not the chemical loop. That's not the issue. The cost I'm talking about just concept. Hold on.
Yeah, understand.
So yeah, I think you're basically you are asking the different today. I'm look at the highlight, the yellow highlight. That's the focus today. Economics not. I think either tomorrow I will have a separate session that talk about techno economic analysis. You will see the whole picture of this. Okay, so I think this is your question. All right, it's not a more. This side you have excess nitrogen. This side you have excess hydrogen. After separation. Yeah, you do need separation. That's you have to because you have separation excess hydrogen recycled. Make sense?
Yeah, understand.
But there's two right loop. Okay, so you basically you have nitrogen loop coming back, you have a hydrogen loop coming back. Whereas in here,
understand.
Understand? So whereas in here, so and then you. Okay, you basically here you need to have what do you call that? H2, N2, and NH3. All right. So then you need a separation and hydrogen nitrogen coming back. All right. So yeah. So basically in here hydrogen nitrogen they're always together. The separation. Okay. I mean doesn't matter. Either on this hyperbolic process you need separation. Here you need separation. You cannot avoid the separation. What you gain is a low pressure operation. 1 bar.
Yes, sir.
Did you remember I showed you the picture about the first reactor in 1909 built by the BASF German company? Remember the big reactor, the wall, 250 bar. The wall is like how many? It's like 8 inch converting to the centimeter. It's like probably the 20 to 25 centimeter. The wall. In order to have ammonia, the Haber-Bosch reactor 250 bar, the reactor wall need to be 20 to 25 centimeter. But here ambient pressure. Actually, if you look at the chemical looping, the example I show you in my laboratory, we actually using the reactor with a closed window. It's ambient pressure. So anyway, that's big savings on the capital cost. Okay. Any question on this one?
No question, sir. We'll move on.
Okay, let's keep on going. Thank you. Thank you for the question. So next I'm going to talk about a paper. If anybody are interested, it's by actually he's my friend. Now he's at Washington State University. So he published the chemical engineering technology. I'm going to email you this paper. And this paper, I think on day 8 and 9, which is today's Monday, I think Wednesday and Thursday, there will be the 3 sessions. I want to use this as case study, this paper, because he calculate to produce 100 kg of ammonia chemical looping. He wants like 1 ton of manganese. So I'm going to interpret his data today, but I will email Dr. Anand this paper. I want everybody do a little bit of homework, pre-read, come to class, and then using his data, let's do a calculation to see the size of the reactor chemical looping. Okay, so just keep in mind this paper I'm going to send to you. Okay, I already downloaded. You don't have to download. I already downloaded, sent to you, but I'm going to interpret what he did. but he didn't use the plasma. He didn't use a microwave. But next couple slides, I'm going to interpret to you about the microwave, microplasma. But I want to give a very basic idea. He did chemical looping ammonia synthesis using manganese as the nitrogen carrier, and then he basically he did ambient pressure, and then he did ambient pressure and also using the sodium as a promoter. So what's the advantage of the ambient pressure, the ammonia synthesis? I don't know if I show you the thermodynamics. Just give me 1 second. I'm going to put the thermodynamics in here. You will see if you do not do chemical looping, if you put hydrogen and nitrogen together at ambient pressure, if you can make ammonia thermodynamically. Okay, give me 30 seconds. I'm going to go to my folder and get you the thermodynamic data. I think I show you in day 1, but I want to cut and paste here. Yeah, then you will understand why ambient pressure ammonia synthesis is so important. Okay, I found it. I'm going to put these here. Okay, found it. Can you see my screen?
Yes, sir.
You see this is the ammonia synthesis, thermodynamics and kinetics. Okay, so look at the left-hand side, thermodynamics. So this is basically the different pressure. And 0.1 means ambient pressure. And then on the y-axis is basically the how much ammonia you can make, ammonia concentration. On x-axis is basically the temperature. Okay, so if you look at this curve, you have to do very low temperature in order to get decent ammonia. If you increase the temperature, let's say 400 degrees C, not even near Haber-Bosch the pressure. Remember Haber-Bosch 450 to 500 degrees C. At 400 degrees C, if you do not increase the pressure, you get nothing. You get zero. This is the reason Haber-Bosch has to go higher pressure and go to different curve. So that's why the Haber-Bosch is operated at the very high the pressure to get the very decent conversion. Okay, so look at this. Ambient pressure, high temperature, passing 400 degrees C, essentially you do not make any ammonia. So I think I showed you this in the beginning. I don't think that was very quick. So anyway, let's come back to here. So chemical looping manganese in this paper, this is ammonia at ambient pressure, but it uses sodium as a promoter. Sodium manganese altogether is how they build this nitrogen carrier, okay? And he used a thermally heated reactor. And here's concept. So he basically put this nitrogen carrier together, and then this is what you call that? The gray color is the manganese, is what he has, and then the N2, which is nitrogen, is black dot, and then going in there. And then that's called the nitridation. What's the meaning of what does the nitridation means? Nitridation means they basically dissociate nitrogen, form the nitride. Okay, form the nitride, and then they become the so-called nitridation process. If you look at pay attention to the cartoon, N2, two nitrogen together, some stay on the surface. Only those go into the bulk, which is the next layer, subsurface, they become the nitride. Okay, see this is a single black dot, it's become nitride. So I make notes here. Dissociate N2 becomes N is present in the bulk of the carrier and the surface. So the surface is N2, and then but majority is in the bulk. Now when you see 700 degrees C, when the atmospheric pressure, the hydrogen react with this bulk form ammonia, but in the meantime, there's N2 come out. You don't want the N2 coming out. You want hydrogen react with the nitride and then become the so-called ammonia. It's called harvest. Harvest means, hey, I form nitride by placing the hydrogen by contacting hydrogen with this material, I produce ammonia. So in the literature they use harvest, but it's more like a production. Okay. So but the side reaction is nitrogen come out. You spend a lot of effort, and then you basically produce the nitridation material, but you don't want nitrogen coming out. You want ammonia. All right. Keep in mind it's ambient pressure 700 degrees C, and then form ammonia. Let's go back to here. Ambient pressure 700 degrees C. What's happening? Can anybody read this curve? 700 degrees C. Do you produce ammonia?
Yes.
No, you do not produce ammonia. You basically subject to this line. This line 400 degrees C stop. If you go to the 700 degrees C, you have nothing. So basically 400 degrees C, you do not have ammonia. And then if you follow this line, ambient pressure, keep on going, passing 400 degrees C, you don't have ammonia. 700 degrees C, you get nothing. So this is the reason, this basically is the thermodynamic equilibrium. This is the reason, remember I asked you a question. Do you think the chemical looping ammonia is subject to equilibrium limitation? The answer is no. Okay, why is no? So this paper tell you the truth. 700 degrees C, they can produce the ambient pressure, they can produce ammonia. But if you look at the thermodynamics, you cannot produce ammonia 400, even 400 degrees C. Going higher, even worse, because this line stopped already. You will never produce ammonia. So this really tell you chemical looping does not subject to here. So basically, the entire curve doesn't work for the chemical looping. Chemical looping does not follow this curve. It's how you break the thermodynamics. Make sense? Anybody have any question? You understand what I'm saying? So basically, this chemical looping produce ammonia at ambient pressure, but you cannot produce this if you use a conventional Haber-Bosch process at 700 degrees C. Conventional Haber-Bosch process, nitrogen, hydrogen, they are together. But here, nitrogen and hydrogen are not together because you do nitridation, and then you form ammonia, and that's the chemical looping process, which we talk about in here. So you have a nitridation, you have harvest. So this is right loop in closed chemistry is shown here. It's how this nitrogen activate is in the bulk phase. Okay. Any questions until this point?
Yeah. Sir, chemical looping and this slide is catalysis. Surface catalysis. Hello, sir.
Chemical looping, yes, you can get a surface, and then but basically very good question. So basically the nitrogen, it just depends on material you use. Surface reaction is typically the so-called what you call that catalysis. Okay, but chemical looping is more than catalysis. This material, which is the nitrogen carrier, is catalyst and also reactant. The meaning reactant means they actually react with the nitrogen to form the nitride. Whereas the Haber-Bosch catalysis, the catalyst structure doesn't change. Here, structure already changed because they have to create a vacancy, allow the nitrogen come in. You follow me? So whereas catalysis, if you do talk about, let me draw some very good question. If you do the catalysis,
catalysis, I mean, catalyst won't involve the reaction, but here in chemical looping, that base metal is involved the reaction, stops the
yes,
reaction. But
that's that's right. So let's say if you have the catalyst, okay, surface. So if you let me draw on this side, okay. So this catalyst. So the bulk of catalyst never react. So basically what you react, so basically your N2 is here on the so your N2 is on the surface. So basically it's called as absorption, not bonding. Okay. I'm drawing the line. Gosh, I cannot draw the line here. Let me leave that. So it's called adsorption on the surface. Sorry, I don't want to waste my time drawing this, okay? Because I don't have to see the N2 on the surface, and then
okay.
So this is the basics of the catalyst.
Bring it to back. Bring to back.
So this is catalyst, okay? So N2 only interact with the surface, okay? This is catalyst. Now the metal nitride is more than catalyst. So the basic N2 go into the bulk, and see this, and then this nitride become they do have the N2 on the surface. See, this is the two black dots. They do have N2 on the surface, but a lot of N2 go inside. So that the whole thing become the reactant to react with the hydrogen. You see, hydrogen not only react with surface, but hydrogen more than likely react with this in the bulk. So the chemical looping is a little different from catalysis because the whole material after nitridation, when you move this material to another reactor, the whole solid they react with hydrogen. You had to see metal nitride as a whole, as a total. Whereas catalysis, you're basically dealing with a surface reaction, nitrogen plus hydrogen. It all depends on how you activate it. So chemical looping is more than catalysis because the bulk of the material participate in the reaction. Any question? Make sense? Does it make sense to you?
Yes, sir. You got it.
Okay. Okay. So yeah, this is really the next. Also from this paper, I cited from this paper. So that's our data. If you read the paper, this is our data. So this is why you run the looping. So see how they did. So they start air, which means the oxides the material is manganese oxide. So then they start a nitrogen, become nitridation. So essentially, actually the nitrogen kick out the oxygen, and then become metal nitride, and then the form. And then I don't. This part I didn't know why they put in a little bit oxygen and then for what. But next section they come in, hydrogen react, and then they oxidize again to rebuild the structure. I think they shouldn't put air in there, in my opinion, because in between the nitrogen and the hydrogen, they shouldn't have anything air going on, because otherwise hydrogen will be oxidized. I think this paper something wrong because I can see they're beginning with the metal oxide, then they do nitridation because nitrogen need to replace some oxygen vacancy. Then immediately they should put in hydrogen, but I do not understand why they put air in there. So I think maybe their student just didn't consider, but they published it. The hydrogen form ammonia, then they basically oxidize again, but they oxidize again, they try to rebuild the structure. and then they do nitridation followed by hydrogen, nitridation followed by hydrogen. If you look at the shape of this curve, this is conceptual. This is not experimental data. Can you guys tell the differences? I'm pretty sure when the student plot this, they only draw the okay. I'm gonna do annotation. Okay. This is not experimental data. This is conceptual data. What they did was they draw only two, and then they cut and paste. Do you see this? These two remaining almost identical to this. This is not experimental data. I don't know why they publish. I think they should publish this using experimental data rather than just conceptual. So you see, I'm going to tell you. Okay, look at my cursor. This one. If you put them together, copy, you get this one. You copy, you get this one. But in the paper, they say they did 3 cycles, but I doubt it because it's just simply like a computer drawing. You guys agree with me? It's such high you can't experimentally you can't repeat this much. The highly you have to have some spikes. So yeah, but in the paper they say, oh, the experimental data, cycle 1, cycle 2, cycle 3. But I don't think this experimental data. It's just conceptual data. Let me ask a question. Can you see this curve? Did you understand what I'm saying? All right.
Yes, sir.
Yeah, it's just so much overlapping. This one overlapping with this one, and overlapping this one, and yeah. So it's how you you review other people's the paper. I tell the truth. I receive the journal requests every day. I don't review so many papers. I only review those the reputable papers from the journals. I mean, if you review enough of the paper, you can eyeball see, oh, if this guy's present experimental data or present either you call the fabricated data or some kind of conceptual data. To me, this is not experimental data because you can't produce experimental data like this. It's always error in between. I mean, there's 3 cycles. How can the cycle 1, cycle 2, cycle 3 such highly reproducible? No way. Yeah. Okay, that's a side story. I'm not going to talk about this, but I do want to send you this paper and having you. I'm going to send to Dr. Anand. I want you to read which page number, do a quick calculation, see how they come up with the size of the reactor. Okay, so yeah. If you have to ask a question, I'm going to go show you another paper. Okay, so this is another paper, but I use this cartoon. I use the first paper cartoon to interpret the second paper. So the second paper published in ACS Energy and Fuel. So they basically says so nitrogen yield reduction is due to no, I'm sorry. Okay, so I'm going to, I think I jump a little bit further. Okay, all right. So it is from this paper, but I used the cartoon from the first paper because this paper from Energy Fuel did not show any cartoon. So in this paper, so they basically saying that if you do that, okay, let me back up. That's why I don't believe this is the experimental data because the second paper from this paper, Energy and Fuel, it says ammonia yield reduction is due to unconverted nitrogen remaining in the manganese and likely the formation of an N2 rather than desired NH3. So two papers, they're basically by 2 different groups. The first group basically publishes data, and then the second group, and then basically the published data use the same thing, but they say the yield decrease. What does it mean? If you look at the experimental data, all this the curve should be declining. Follow me. So the first cycle and second cycle, third cycle should be declining. That means you cannot rejuvenate or rebuild the same structure because they will not go back. So the reason they cannot go back is they have this the picture, ICM picture. If you see the beginning, look at the picture from the beginning like this, and then in the second cycle like this, third cycle like this, they're changing, right? So kind of if it's a really catalytic process, you will not it's called ICM image. I think everyone understand ICM, right? Scanning electromagnetic microscopic. Okay, ICM. ICM, you can see the surface. You see the surface, cycle 1, cycle 2, cycle 3, they're changing, all right? So they shouldn't change, because if you change, that means the yield will be declining because they cannot go back to the original. So that's why the second paper reported the yield decreasing. So then why the yield decreasing, they interpret it. So this cartoon is from the first paper, but they use their cartoon to interpret. Why they interpret? Because the reason yield decrease is an N2 coming out. You desire the product is ammonia, but your N2 actually they keep on coming out because this is the so-called bulk, the nitrogen does not go to the ammonia, they go to N2. That's why the ammonia yield decrease. It's a little bit complicated. So that's why when you run the chemical looping, every cycle the material undergo the structure change. Look at structure, they change. The different cycles, they change. So that means every time they change the structure, they affect their yield. Affecting their yield means they're decreasing. The interpretation of affecting the yield is basically nitrogen come out rather than ammonia. Make sense?
Yes, sir. So once its temperature is getting increased, it means the surface morphology getting changed.
Thank you. Yes, it does change. It's morphology change. Yep. So that's why it's very difficult. By the way, remember this picture 700 degrees C. I think at the beginning I show you. I haven't talked about microwave or plasma. They're thermally heated reactor. They use just conventional heating, but they have to operate 700 degrees C. As you said, the morphology keep on changing. So that means it's just conceptual. It's not like this. I can tell you experimentally how it look like. Basically, it should be declining.
Yeah.
You see my curve? It should be like this. And then the first paper, which I'm going to send to you, didn't tell. They just say, hey, the result, which I don't believe it. Then I keep on searching. I found a second paper, and then they said, oh, the yield reduction is due to this. They basically interpret what's going on, which is good. So I mean, that's why in the open literature, you want to read more paper to see how different people say something differently. Okay. So anyway, because the morphology change, like you say, look at morphology change. The morphology change, you cannot go back to original. That means you cycle 2 is not going to be the same. You basically just declining, which is if you look at this ammonia yield, it keep on decreasing.
Then efficient life cycle or efficient lifespan of catalyst. What is the efficient lifespan, sir?
Could you repeat your question again? Is that what's the question again?
Stability of the catalyst.
What about the stability of the catalyst, sir, and as well as lifespan of catalyst?
No, it's about that's why the chemical looping ammonia synthesis is still in the infant stage. You need a material, so you need a very good material, stable. You need to run this couple thousand cycles. Okay, not just one cycle. You need to run a couple of thousand cycles. Otherwise, if you only run 3 cycles declining, you cannot commercialize it. So it's still in the early stage. They call it infant stage. So there's a lot of material science behind this, and then you have to develop this. One of the reasons I can tell you, you can solve this from engineering point of view. Okay, so very good question. So you can solve this issue, declining issue from engineering point of view. I hope I solved it. Okay, so read each bullet. I have 4 bullets in here. So let's go back here. Let's say you have a nitride, okay? So if you put a nitride in here, and then if you deplete all this nitride, okay, look at my circle. You did all this nitride in the bulk from ammonia. Let's say I made it up, okay? So let's say the equivalent to 10%, okay? So when all this come out, I would say theoretical. So let's say theoretical yield equals 10%, okay? So 10% ammonia. So that means O N nitride. Okay. So let's say the theoretical use is 10%. Make assumption. So that means all this bulk nitride turn into ammonia. So what's the problem? Keep in mind, I think you just asked a very good question. So this is bulk reaction. This the morphology changes, all right? Nitrogen actually exchange the position with oxygen. They form a structure in there. Actually, they support the morphology structure. You have all this nitrogen coming out, the structure collapses, all right? Because you don't have any supporting material. Make sense? So let's say if theoretical use 10%, in order to run this chemical looping, do not deplete the nitride in the looping process. Depleted means do not let 10% nitrogen come out. You do 5%. Follow me? Or 3%. Then you do the next looping. Always keep nitride in there, some nitride to hold the structure. Otherwise, your morphology will change. Make sense?
Yes, sir.
It's a structure. Basically, in chemical looping, when nitrogen get into the structure, they hold your morphology. They keep it. So that's why the nitrogen carrier is reactant. If you all of a sudden pull out the nitrogen, and then basically the structure has nowhere to go, they collapse. That's why you see all of the structure change. So the rule of thumb in chemical looping is do not deplete nitride. You have that's why I'm going to send you the paper. I want you to calculate theoretical yield. What's the theoretical yield? And then once you know theoretical yield, you have to control. Probably you need to you do not deplete it. Every time you just like probably 30 or 50% of nitrogen come out, keep some nitride in there. Then you replenish nitrogen to 100%, and then do the next cycle. So you always have nitride hold the structure. If you have everything come out, you probably run 1 cycle or 2 cycles. Let's say the material the stability drop. So this is really the engineering solution. But regardless, you need to have very good material. That structure, the morphology never change. So you can run couple thousand cycles. I think that you asked a very good question. So there's a lot of engineering solution. There's also material science solution. But chemical looping is still in the infant stage. Look at the second bullet. Chemical looping is different from catalysis. Catalysis is a surface reaction, but chemical looping is a bulk reaction. Okay. So a bulk material participates in the reaction. So what does it mean? That means you cannot deplete all the nitrogen in the bulk. If you deplete it, sorry, it's gone. So the number 4, in the chemical looping world, there is basically the modeling, the so-called modeling work is very complex. So the modeling work is so complex. It means it's a very difficult to model. I will tell you why. So I think we only have a couple minutes. Okay. Well, before I tell you, maybe we'll go to shrinking model tomorrow. And I think I'm glad that I have so many slides prepared. So tomorrow I'm going to continue chemical looping, now the microwave, and then how microwave compared to thermal. Remember the paper we are talking about, last two paper, they are thermally heated chemical looping. But now I'm using microwave, which is my work compared to the thermally heated chemical looping. So different heating mechanism. You can see the advantage of microwave. Then tomorrow at the end, I'm going to talk about how the microwave plasma induce or enable chemical looping. Okay, so tomorrow we have quite a bit of presentation. So I thought I can finish today. Then at the beginning, when I sense the audience doesn't even understand the chemical looping, I slow down quite a bit. So I'm glad that you understand, because I have to give you background on the chemical looping. And then it starts from combustion, oxygen combustion, then come to here. Okay, so this is going to be tomorrow. I think I'm going to stop here. Dr. Anand will send you the paper from the Peter From, the one. So I will have read the paper. You don't have to read the whole thing. I will tell which page you need to read. But I want you to calculate, see if you come up with the same conclusion as the paper. Yeah, the paper skips several steps. By reading paper, I want somebody just the whole audience pre-read. But that will not be for tomorrow. That will be for Wednesday and Thursday. Okay, so tomorrow we'll continue this, because I have a lot of things to talk, because I haven't talked about separation, low pressure separation. We need to talk about the technical economic analysis, and also the ammonia membrane. So we have quite a bit to talk, but I don't want to rush, because if I can run my slide, you never understand. So that's why I slow down quite a bit, because the goal is not just finish my lecture. I want to make sure you understand. Even if I only lecture half of my material, I'm happy if you understand even like 30% of my presentation or my lecture. Make sense?
Yes. Yes, sir.
Okay. So I would like you guys, I know you have long day. I mean, it's very intensive courses. Every day you have like a full lectures the whole day. So I will have you to take a break, and then I will see you tomorrow. Okay, tomorrow we'll continue this. Yeah. Okay. Thank you.
Yeah.
Thank you, everyone.
Kind words, sir. Tomorrow meeting, sir. We will
tomorrow, I think my session starts from the same time. I have 2 sessions tomorrow. Yeah. Wednesday, Thursday, I have 3 sessions. Tomorrow, I think the Dr. Anand will send the link, and then the 2 sessions tomorrow. Okay. For me, yeah. So okay. All right.
Sure, sir.
Okay. Thank you, everyone.
We will share the link to you, sir. Tomorrow's link.
What'd you say? Yeah. You will send me the Zoom link. Is that right?
Yeah. We will share it.
Yeah, send you. And also, I'm going to email Dr. Anand the paper, and then I will tell you what calculation I need from you. Basically, I want you to repeat his calculation. I don't believe his calculation is right, that paper. It's good. I think you read the paper and you criticize that paper and then come up with a solution based on knowledge we learn. Okay, that's why I don't believe it. I mean, we all know that, right? Whatever published literature, they may not be right. That's why the science has to be good. One people publish paper, you publish, and another publish. So then you build a knowledge base. So nothing wrong with I don't think that paper is wrong. It's just because they are in the early stage. So there are a lot of things probably they haven't thought about it, and later on people say, oh, it should be like this. So I want to send you a paper, having you criticize that paper and come up with a calculation. Okay. Thank you, everyone. Yeah.
Thank you, sir. Thanks for your yeah. We'll meet tomorrow.
We'll meet tomorrow.
Yes. Have a nice day.